Hi everybody. So today I want to talk about capacitors. And really the way I remember capacitors, I don't necessarily directly remember them. I just remember that a lot of what they do is sort of like um, opposite of resistors. You can also look at, or well, that's in certain situations. You can look at capacitors as sort of like, okay, so let me say this first. What a capacitor does is it stores charge. So I sort of look at capacitors as like batteries in a way. They're sort of like fake batteries. Okay, um, but there's a lot, and it's not just in like setups that I use resistance to remember them. It's also like formulas. Okay, and I'll explain why. The first formula you need to know is the basic formula for capacitance. I really don't say to memorize things too much, but I mean, this is probably something that you'll just have to remember. Um, this is obviously given in units of Q, which would be charge, over V, which would be volts. But we call this a farad, okay? I think the person probably who discovered capacitance, their name was Farad, their last name. So that's my guess. Um, Another formula you need to know. Now remember, we had two formulas for resistance as well. That I mean, there are probably more. I just don't know them. But there are two basic formulas, right? This we also have two basic formulas. Um, so the next formula you need to know is E naught multiplied by A over D. And this E naught, you might recognize it. It's the permittivity of free space. So I want to draw maybe like what I imagine a capacitor to look like, right? This is it, and maybe charge is like stored in between, right? So like on a circuit, you might see a capacitor look like this. Literally, it's just two straight plates, right? You might have maybe like a resistor going somewhere or something, right? That's what a capacitor looks like, okay? So what a capacitor does, it stores charge in between its plates. This distance right here is the distance between those plates, okay? Now I want to mention that this A is the area of overlap, okay? The way I look at it, one capacitor has a positive plate and a capacitor has a negative plate, right? So I sort of look at it as like to hold charge, right? And I don't know if this is the correct way to look at it, but this is how I remember it. It holds charge, right? So maybe like the further apart you go, the less easy it is for like that attraction between the positive and let's say this is the positive plate, this is the negative plate. That attraction for the positive plate and the negative plate to hold that charge comfortably, right? Because there's as the further apart that these two plates go from each other, the less that strength is between the two plates. That's the way I look at it. The greater this distance gets, right? The smaller this C gets. That's the way we look at it, right? But at the same time, I also look at it, we said the area of overlap, right? So I imagine that it would be this whole area of overlap here, right? You can't make this area too small because if I had a capacitor that maybe looked like this, the only thing attracting is this area right here, right? Even yes, this could be positively charged and negatively charged here, right? We could say that. But really there's gonna be nothing held in between here, right? Why would there be? So the charge can't be held here. So the greater you make this area of overlap, if I bring this whole thing down and then say, okay, cool, we have a greater area of overlap now. I look at it as more charge can be held between those two plates. That's how I look at it, okay? And I also want to point something out. I want us to take a look at the formula for resistance really quick. And I want you to remember that first formula I gave you. Rho over L times A. Now, if we look at this formula, that rho is like, it's a property. While, yes, this is a constant, right? The permittivity of free space is always the same. But let's say I took that as, I mean, technically, if we're dealing with other materials, this is like with a certain material, this is always going to be, right? It's got a certain resistivity, right? So this E naught and this rho can sort of be looked at as the same. But remember, I said the resistors are opposite, right, of capacitors. At least that's the way I look at it in my head. This length is at the top, while this length is at the bottom. and this A is at the bottom while this A is at the top. So isn't that sort of opposite? So capacitance, in a way, is sort of like, I use it to remember it as it's the opposite of resistance. Okay, that's a good way to look at it, I think, at least. Maybe not, but the next thing you're gonna need to know is, so you've probably heard of a formula for electric field, maybe taking into account charge and everything. This one here is for the electric field between like parallel plates that may occur, is the voltage over the distance of those plates. So that's something you need to remember. Capacitance also have a potential energy. So in a way, like capacitance, potential energy is like the potential to do work, right? So that stored charge in a way gives us a level of potential energy. And I use kinetic energy, the conventional formula that we might think of for kinetic energy, to remember this. Remember, kinetic energy is half mv squared, right? For capacitors, it's half cv squared. So kinetic energy, might be a good way to remember that. Okay, so that's just the potential energy of it. And when you do the units and everything, you get volts. I think a good thing to also talk about is dielectric materials, and this is how this is spelled. Dielectric materials. Basically, dielectric is like another word for insulation. You're gonna need to remember this formula. It's C prime is equal to K. That should be a small k. Let me say that. It's actually kappa times C. So this C is capacitance, right? This K is the dielectric constant, and this C prime is like, it's also capacitance, but like it's like your final capacitance once you've introduced the dielectric material. So a lot of times, maybe let's take like just a basic capacitor. Let's say there's air in between it, right? This K is gonna be 1 point something, 1.0 something, I think. It's not that great once you look at other numbers. Glass, for example, is 4.7. So when you have material in between a capacitor, in between the walls of a capacitor, or the ends of a capacitor, right? Let's say this space is filled with like glass, right? I don't know if I'm drawing it properly, but just imagine like it's filled with glass. I look at it as there's charge more easily held in this space because there's something to hold that charge now. The electrons have like molecules sort of to attach to, or I don't know if that's the correct terminology, but that's the way I look at it, right? In a vacuum, for example, the dielectric constant is 1, and that's where this goes to 1, right? And then in that situation, C prime is equal to C, right? And that's a lot of the time, like we might be just pretending like there's a vacuum or something. But the second you introduce maybe air or like some other maybe solid or something in between it, right? You're gonna notice that that dielectric constant is gonna go up. So that's a good way to put it. So to increase the capacitance, you want to put things with higher dielectric constants. Yeah, I think we're gonna go ahead and stop there. Next time I'm gonna talk about how to like look at capacitors on like a you know what? Actually, you know what? Let's just talk about it right now. So basically, remember we talked about resistance in a circuit, right? You also have capacitance in a circuit. So let's say I have a capacitor that's set up like this. And let's say I want to find the total capacitance, right? Now, what I'm going to do for a series circuit, remember I said capacitors are the opposite of resistors, right? You've probably already guessed it. 1 over the total, the equivalent capacitance is equal to 1 over C1 plus 1 over C2. You can also, and I'll say plus 1 over C3 plus all the way to 1 over Cn. Okay, and that's N being the number of capacitors that you have in a setup. Now, that if it's only 2 capacitors, you can use that same formula to get you directly your equivalent capacitance, so that you don't have to start taking the reciprocal and everything. Okay. Now, for a capacitor in parallel, you've probably already guessed it. If I had a little setup that looks like this, and I think that's just another sort of just, it's intuitive. This is a straight. These plates are the same length. That's how you draw it on a graph. Excuse me. That's how you draw it on a graph, right? This plate is slightly longer than the other. This just like, it's just like, oh, positive, negative, yeah. But like, that's another way to remember a capacitor. Maybe store some type of charge or energy or something like that, right? It's sort of similar to a battery as well. That's what I'm trying to say. But if I have parallel capacitance, you just do this for now. That capacitance, literally, you're just gonna add them up. So like, let's say this is my C1, this is my C2. My capacitance is gonna be equal to C1 plus C2. Simple enough, right? Now let's say I wanna like add in another part or something, and I wanna find the equivalent capacitance of the whole thing, right? I'm gonna go ahead and say, I'm gonna go ahead and convert this to another circuit, and I'm gonna say something like this. Oops. Where this is my C1 times C2 over C1 plus C2, because this is my equivalent capacitance. Once I've turned these two into one capacitor, which becomes this, that's what I end up getting. And then this is my, oh, I'm so sorry, I did not mean to draw a resistor there. That is actually meant to be a capacitor. Then this is my C3, okay? So my total capacitance for this will be C1 times C2 over C1 plus C2 plus that C3. And that's going to be my total capacitance. I think we're going to go ahead and stop there. Hope this video explains